The weird thing about AI is how weightless it feels. You type a prompt, you get a good reply, and you think to yourself, wow, this all happened on the cloud. But the cloud isn't a cloud. It's a warehouse known as a data center that turns electricity into math to reply to one of your questions. And behind that one reply is a data center drawing more power than a small town. I'm being serious. In 2023, when AI was just starting out, the US Department of Energy says that US data centers used about 4.4% of the total US electricity, which was around 176 terawatt hours. Now, by 2028, US data centers are projected to reach a low range of 325 terawatt hours to a high range of 580 terawatt hours by 2028, within 5 years. That is an 85% increase in power in just 5 years. Side note, by the way, terawatt hour is actually a large unit of current, very, very large. 1 terawatt hour can power about 90,000 houses for a year in the US. So data centers use a lot of power. And this is not a problem that the government can say, oh, we just need to optimize our grid. We just need to tell people to turn off the lights when they're not in the room. This is we actually need to build new power plants problem. But the biggest issue, and the issue that I feel isn't really spoken about at the moment, is this. If we release an AI model that is 10 times more advanced than the previous model, it doesn't mean that it will only need to be fed 10 times more electricity. It means that it will probably need 100 times more electricity than the previous model. It's not a 1-to-1 ratio. And if you don't believe me, there is some proper math from OpenAI themselves to prove it. In 2020, a team at OpenAI published a paper. The paper was called Scaling Laws for Neural Language Models. And it was interesting because they studied how large language models, the AI, can improve when you increase 3 things. The 3 things being the size of the model. So basically how big it is, how many parameters it has, the amount of data that it is trained on, and lastly, the amount of compute. So when I talk about the compute of a model, it just means the number of math operations it can run. And what they found is that AI performance does improve when you throw more resources at it, like giving it a big brain, giving it more time to learn. But each time you double the resources, you don't double the improvement. You get a tiny improvement. And in math terms, the paper looked at something called the model's loss, which is a measure of how wrong or off the AI is. It's like a measure of error. And they found that AI follows a power law like this. So L is the loss, how much the AI is off by, the error, and you want L to be as low as possible. And C is the total compute used during training. The others are just mathematical constants. And what the formula tells us is simple. Each time you increase your compute, your improvements get smaller and smaller. So at the beginning, you can train a model and cut the error in half. Great. But later, you might need to double or triple your compute just to get a tiny improvement. So now, if AI companies want a smarter model, they can't just spin up more servers, they have to start building data centers. To add to that, in 2022, Google's DeepMind published another famous paper, which also showed another twist. They found that the biggest models were actually being trained inefficiently. The models were in fact too big for the amount of data that they saw. And if you read the paper, their conclusion basically says, look, if you do want to double the model size, if you want to give your model more brain power, you also need to double the amount of experience you feed it. Otherwise, you're just wasting your time. You're wasting the compute. And this finding, unfortunately, doesn't reduce energy costs. It pushes them up. Because now companies want to run bigger models, they want to make the model smarter, but they also need to give it more data. So you're running them for longer and over more data. So energy use scales up, not because the AI is smarter, but because we're feeding it more information, more training runs, more electricity. But wait, there's more. Modern AI isn't running on servers the way that your 2012 web apps used to run on servers. It's running on racks that look like really heavy industrial equipment. So for example, NVIDIA has this high-end AI infrastructure for their enterprise clients. It's called the NVIDIA DGX SuperPod ecosystem, and it looks like this. So this infrastructure for AI runs on racks, and the rack power consumption is approximately 120 kilowatts. And this is just one rack. If you look at older enterprise data centers, one rack a few years ago was about 5 to 10 kilowatts. That was what was normal. Now we're talking about racks that use 12 times more power. And the other thing that people often forget about is that all electrical energy that goes into compute becomes heat. And that heat has to leave. You can't negotiate with thermodynamics. So if you put 120 kilowatts into the rack, you need to remove roughly 120 kilowatts of heat continuously. Or you don't have a data center, you have a space heater that may just output some text on occasion. Now, according to the International Energy Agency, cooling systems for data centers can account for 7% of the total power bill if the data center is highly efficient, new, and modern. However, in older data centers, cooling systems can be up to 30% of the total power bill. So between 7 to 30%, that is still a large amount of power that you need for cooling. It's not really a side issue, it's a major slice of the pie. There's this key stat that makes it all visible, and it's called PUE, Power Usage Effectiveness, and it's a simple ratio. So PUE equals the total power used by the facility divided by the power used just by the servers. And in 2024, Uptime's Institute released this report that said that the industry average PUE is 1.56. So this means that for every 1 watt going directly into the chips doing the computing, another 0.56 watts, more than half of that, goes to everything else. Cooling systems, fans, powers, converters, backup infrastructure, whatever. A significant part of the AI energy bill doesn't actually make the model smarter. It's just keeping the hardware from catching on fire. So AI doesn't only need computers anymore. It now needs more plumbing, it needs more pumps, it needs more power shelves, it needs more water. But wait, there's still more. So we know AI is using a boatload of power, water, heat. But to add to this problem, AI infrastructure moves at fast speed. Power grids, however, move at construction speed. So according to the International Energy Agency, a modern data center, the kind that is built to train and run large AI models, well, these can be up and running within 2 to 3 years, from design to operational in 2 to 3 years. But the electrical infrastructure needed to power your AI centers, so the cables, the transformers, the substations, they can take twice as long, or even more. In some countries, just getting approval and building a transmission line, that takes about 4 to 8 years. In my country, it's not going to come because we don't have power in the first place. But this means that companies can buy millions of dollars worth of AI hardware, racks, really ultra-powerful processors, and have them installed and ready to go. But companies now will have no way to plug it in. In the US, this is already creating tension. I do speak about the US a lot because obviously they are at the forefront of the AI industry. So there's an organization that oversees electrical reliability called NERC. And they state that the demand for new energy is surging after years of very flat growth, which is really interesting. And data centers are actually leading that charge. I spoke about it earlier, but in 2023, data centers accounted for 4.4% of the US's total power bill. By 2028, it's projected that they will be around 12% of the total US's power bill. That's a lot. That's a large increase. And remember that these facilities pop up in clusters. They're not normal. These AI facilities would want hundreds of megawatts at one specific time, which is equivalent of adding an entire city's worth of power in one step. And that's a big problem because power grids aren't really designed to handle that. We haven't had that issue before. If you look at traditional use of electricity, so in homes and offices, it's fairly predictable. It goes up in the mornings, maybe it peaks in the evenings, and it changes because of seasons. AI workloads are not the same. They are very unpredictable, and they are driven by corporate strategy, not consumer habits. So a company might decide to deploy a massive training run overnight, which means that a quiet region could suddenly need enough power for a city, all because of one data center. And you can see the stress showing up in official planning. There's a national grid report by Grid Strategies, and they show that multiple US regions are actually rushing to build high-capacity transmission lines. And these are huge projects in areas like PJM, which is the largest grid operator in the US. And if the grid can't expand fast enough, well, the tech industry often builds around bottlenecks. According to Reuters, the tech companies are considering building massive data centers next to their own private power sources, or even sign massive deals with electricity utilities. But I think we know that when large companies actually start to do these side quests, often they'll do sneaky things, they'll skip laws, regulations as well until it is regulated again. It's just very unlike them to do what's best in the public interest. But now, at this stage, you're probably thinking, all right, so what now? And to be clear, the risk isn't that the world will run out of electricity tomorrow. And according to the IEA, even in a strong growth scenario, AI data centers will only account for just less than 10% of the global electricity demand between now and 2030. So globally, we won't face an issue where AI will completely destroy the power grid. Obviously, if that happens, governments will just shut off any AI data centers. But the real risk here is local and it's structural. When I say AI infrastructure is approaching a total meltdown, meltdown means that in places where AI data centers cluster, maybe near fiber lines, urban areas, existing campuses, the local grid may not be able to keep up. And then projects will start to stall, but prices will start to spike around that area. There's also going to be a new stress on the load. That is another meltdown. These AI loads don't behave like traditional demand. They're unpredictable, they can often be massive, and they can appear suddenly. Grid operators are actually used to managing morning peaks, evening loads, seasonal swings. They're probably not used to handle overnight requests from a data center that suddenly needs a city worth of power and they need it now. And costs show up in strange ways. So yes, the AI industry would want an advanced model. It would want advanced AI. But now we need the grids to be scaled up. We need new transformers. We need new transmission lines. Then scaling AI becomes less of writing software and more of, oh, we need to build a factory. The big issue here is that AI is using a lot of energy. It's using a lot of power. I mean, a report just came out. I've just added this to my script, where creating a 5-second AI video is like running a microwave for an hour. And if you can imagine the content farms that are using AI all over social media, it's just a lot of unnecessary power. I think the bigger question that lawmakers need to ask is, how long are we going to treat AI as a software? Because it really isn't anymore. Thank you so much for watching. If you like my content, please like, comment, and subscribe. I will see you on the next one.